Hi everyone, thank you for joining this conference and this session. So I'm Julian, I'm working as a technical specialist for Microsoft, so technical specialist on NoSQL solution mainly. I'm with Rumen today, who is a senior cloud architect for Microsoft too. So today we will speak about an existing customer who did the migration of PostgreSQL to Cosmos DB. During this session, we will have several parts. So, of course, Rumen will start by presenting the application and the driver of the migration who leads the customer to move from PostgreSQL to Cosmos DB. I will then speak about the differences between relational databases and NoSQL databases and the different phases of this project. And then Rumen will speak about the different lessons that we learn during this project, and sometimes hardly, and the useful resources that you can use if you want to reproduce the same.
Hi everyone, this is Rumen. I would like to present you the application that is designed to be migrated. Initially, this is an application that is mobile application for well-being, and has been used by tens of thousands of users. And the customer wanted to migrate it to the cloud in order to scale it to the global scale for tens of millions of users. Initially we start with the lift and shift just to move all the applications and microservices and database to the cloud. But then, meanwhile, we decide that modernization also will be necessary in order to address some of the goals that I'm going to explain a little bit further. The whole architecture that you see here is the architecture to be, the one that is in the cloud, not the one that is on-prem, but in general it keeps the same ideas. One of the changes, for instance, is introducing sensitive data database, which is conformant to the regulations and to the requirements, government requirements for keeping personal data. Because we're talking about well-being application, obviously there will be some personal data kept. In general, you can see here that after the migration with the Azure Data Factory, the data is split into two parts. One is in the globally replicated non-sensitive data, which is the majority of the data, and small portion of data, which is the personal data like steps, night cycle, or weight, or calories, and things like that, which are protected through our service, which is called the Fire API, and which is a service for managing healthcare data in a secure and compliant way. Okay, the app service is running the existing microservices which are migrated as they are, and the RabbitMQ on-prem has moved to the Event Hub, also geo-replicated. So using the Global Traffic Manager, we route the traffic to the closest deployment for the user, achieving low latency and high performance. Of course, all these will be possible because of the Cosmos DB capabilities for that. So the drivers for this migration was that the customer wanted to modernize the application from, let's say, enterprise scale, tens of thousands of users, to tens of millions of users to the cloud, to make it public, to make it more available, multiple regions. And that also requires that the application also is modernized to become more scalable, so-called cloud native applications. And one of the requirements is that those kind of applications supports agile development, fast time to market, which needs in the corresponding way to the data to have a flexible schema. So if you have a mobile application that introduces new features, new options, new capabilities, that's not very easy to achieve with the existing Postgres database because of the flexible schema. The second thing is that the platform currently is based on 3 different databases. The majority of the data is placed in the Postgres, but some of the data is also placed in Mongo, which is keeping the persistency of the messages which are exchanging the microservices, and Neo4j for the graph database for their recommendation engine. So in total we have 150 tables in PostgreSQL, which we migrate to just about 20 containers. So this simplification is very important in order to have the same operational capabilities, because Postgre, Mongo, and Neo4j have a different operations and different maintenance. Here with one Cosmos, you have one account which you manage the same way with the same monitoring, let's say, or the same operations. The third one requirement was to have globally scale availability and performance, which is not easy to achieve with the open source version of the Postgre, although there are some commercial off-the-shelves which are built on top of the Postgre, like Citus. It's still the globally availability and replication is not easy to achieve with Postgres, which is built as an enterprise database, not that much as a cloud database. Also, the performance of sub-10 millisecond latency and high scalability are not easy to achieve with the Postgre. So the requirement to have a database that is easy to scale, it is globally available, and it's very close, as close as possible to the customers in the world, was one of the key requirements. The very last one, but also not less important, is the conformance with the healthcare industry. As I mentioned, there are a certain amount of regulations and requirements for keeping personal data, GDPR in Europe, high trust and HIPAA, which are specific for healthcare standards. They are not out of the box supported by Postgre, so it's a lot of efforts to achieve this kind of certification in order to deploy such kind of solution in Europe or other geographies where those are required. So that's coming out of the box with Cosmos, and that's one of the requirements why we migrated to Cosmos. Now my colleague Julien will explain you a little bit more between the differences of the databases. Please, Julien.
Thank you, Raymond. So let's start first with, of course, a well-known 3 V's that we can find in big data world. Of course, volume, velocity, and variety of the data. So everyone knows, since years now. So the world of the data has changed. We have more and more data coming from everywhere, different kind of systems, and of course, the volumes of this data have drastically increased during the past years. And honestly, because I work with both, I can say relational databases are very well, built databases, to manage, complex relationship between entities, to build complex queries, to do some kind of analytics on the data with pre-aggregation and so on. But the problem is, when you are building, complex queries, and mainly because you are using joins between different entities, so different tables, it means that when you need to scale and to increase the volume of the data, and so the volume of data that you are getting back from your queries, of course the performances will decrease. And NoSQL databases have been built from the ground to respond to this kind of problematic. And it's of course there is a counterpart, which is that we need to have more simplicity in the query engine, more simplicity in the type of data that in the data model or the data that we are storing. But by default, NoSQL has been built to store, some kind of documents in different formats. It can be JSON, it can be table-like or column-wide family key values. But it's just, smaller documents, smaller data that can, of course, because the system is not using complex queries, that can grow almost infinitely. Second thing is, of course, the velocity. So it means, globally, the performances. So not just the performances of the data of your queries, but it's also the capability to be able to manage the evolution of the data. So the change of your data, because we are changing information into the database, and the frequency of change of this data, and the frequency of evolution of this data, and the growth of this data into your database. And NoSQL databases are really built to be and optimized, to be able to manage heavy write workload on the system. So to be able to support, millions of reads or writes per second into the same database. And the last part is, of course, the variety, meaning that we are storing data coming from different systems in different formats. And we know that in relational databases, we don't have this kind of flexibility by the fact that we have a fixed schema of the tables, and so we have columns. And to be able to store different type of data into this fixed schema, we need to use some kind of workaround by storing new values into the empty cells. In NoSQL databases, it's not the case because you store JSON documents most of the time, or documents, and these documents can have different forms. So you don't have any schema which is enforcing your data, and so you can store schema or documents with different structure into the same collection of tables, call it like you want, without any issue. And the system is built, in fact, with a weight managing indexes to be able to manage this different type of documents in a performant way, of course. So when will you choose to use NoSQL or relational databases? It's really dependent, on the project and on most of the projects we are seeing. In fact, we are seeing both solutions, and both solutions are working together. But most of the time, when you know that you have, you need to ingest a lot of data, you need to change frequently this data. You don't need to have any schema, or at least you need to be free to store any kind of data into the same database, and you know that the volume of the data will grow. So NoSQL is definitely what you are looking for. If you are looking for performances and also availability, because we have in Cosmos DB, for example, we have by default 99.99% of availability of the platform, which is already very high. You can go to 5 nines if you need. It means that your system is always on. Which is very important for some customers like e-commerce, like banking or so. If you need to manage, complex relationship between data, if you need to have a schema and to enforce a schema for this data, and to be able to do some, as I was saying, some analytics, aggregation on the data using join and so on, relational databases are definitely the choice for this kind of need. But what you can see, it's basically you have different type of NoSQL databases: key value store, document store, column family like Cassandra, for example, and these different kind of databases, or your graph databases also, are all part of the NoSQL world, and it's fitting well, with social network, when you have a lot of messages coming at the same time, with gaming, when you have a lot of players connecting to the same platform that need to chat together, that need to display or to share their dashboard or this kind of things. And of course, when you need to have availability of your database, because you cannot, you need to avoid to have any interaction of service into your game, otherwise you will lose your player. Or IoT, because you have a lot of sensors, sending information at the same time into one data store. It's very interesting to have a NoSQL solution for that. And the other side, you have, of course, the SQL and relational databases with different tables, relationship between these tables. And it's, of course, fitting very well, and it's working very well. I'm seeing a lot of websites working with MySQL, for example, or e-commerce sites. It's working well, for storing, data marks, so very structured data into the systems, and when you need really to enforce the schema to be sure that all the row will have the same kind of information into field globally. So for enterprise, of course, SQL or relational is the best fit. But as I said, both can work together. E-commerce website, you can have a relational database to store some information about the customers, and you can have a NoSQL database to store the product catalog, because all the products don't have the same information, or to store what you have stored into your buckets, for example. So everything can work together for the different function of your application. So just to summarize a little bit more, globally, you need to have scalability, you need to have flexibility, and of course, high performances. NoSQL is the choice. You need to be able to do transaction between your documents, to do joins. You need to do. You have maybe some specific needs in terms of security, complex security. Relational databases will be the choice. And if you need both, globally, you can mix, relational and NoSQL, depending on the function of your application. Some part will go to NoSQL, some part will go to relational. It's definitely not an issue. So to speak about the project itself, and the different steps that we have followed for this project. It was an existing application with an existing database, so we started, of course, to review what the existing things, so existing tables, existing relationships, so to do some reverse engineering about the database, so to discover all the schema and the complexity of the schema of the data, and to be able to think about how we will move this data into another kind of system, into a NoSQL kind of system. And so to do that, in fact, we use an approach which is a domain-driven design to say that we will, in fact, group information together based on the business domain that is related to. And so we will create in Cosmos a container where we will, most of the time, it's not the case for all the containers, but let's say that we will try, in fact, to have one container by business domain and to group all the information coming from PostgreSQL, from the different tables that we have in PostgreSQL, try to fit everything into one specific container, and this is what we have been able to reduce drastically, the number of containers into Cosmos compared to the number of tables that we have in PostgreSQL. And then we went to over all the tables and to find, to group these tables together, to identify the relationship between these tables, and to define what will be the best approach into Cosmos DB. Will it be to embed data together into one document, take data coming from different tables and just build a big JSON documents with all the data together, which can be very interesting when you have a ReDB workload, when you want to do just one query to get all the data together to display in a screen in your application. Or we will try to use a reference approach, saying that we will maybe split the data into different smaller documents and reference this document together with a specific property. And this can be very interesting, when you have more write-heavy workload, because you want to write, small document together, and you don't want to have to update all the time a big document. And it's better to update, small pieces of data. And then do we need to use both at the same time? Because most of the time you will have to use both, and when you need to use both. Second part is, of course, the partitioning, because Cosmos DB is a distributed system, so it means that it will distribute your data into several physical resources behind the scene, and so we need to be able to distribute this data evenly into the system to be sure that we are using the full capacity of the system. And so to have a good distribution of this data, you need to define what will be the best partition key for each of the container based on the type of queries finally that you will do on the system. Because to optimize the queries, in fact, you need to use in your queries ideally the partition key of your data. So when you are doing a query, the system directly knows in which physical resources it needs to go to give you the data, and this is where you will have the best performances, and we will optimize the cost of usage, of course, of Cosmos DB. And so for the queries, we had also to be able to translate finally all the queries that we had in the application using PostgreSQL into queries using the SQL syntax that we have in Cosmos DB, which is not the same syntax as you can find in a relational database. It's not a SQL, so there is limitation that we will see later. And so we need to be able to translate this to use the new data models that we have in Cosmos in an efficient way, of course. So this is maybe one of the tricky parts, because migrating the data is not so complex. When you already know what is the data model globally and you understand the business needs, it's not so complex to have the migration of the data. But to be able to rewrite existing queries and sometimes complex queries into something which is simpler in Cosmos, it can be so tricky sometimes. So for the migration, we use Azure Data Factory, which is a tool that you have in Azure, and you can create your own pipelines with different steps into your pipelines. Take data from one table, join it with another table, do some aggregation, transform the data, and so on. And then you can have different sources like PostgreSQL and destination like Cosmos DB. And the last part, which is another phase of the project. So first phase was to move the data and to refactor the data. The next part will be, of course, to change drastically the application to be more cloud-oriented application. So today we have a microservice approach, and we will try to move also more to using Azure function and so on to go to a serverless approach. But this is another step. So just to give you an overview of origin of the data and where we started from. So as you can see, we had a lot of different tables with different complex relationship between the different tables and entities. And we use Azure Data Factory to have this kind of result in Cosmos DB. So what you can see on the right side is definitely, a smaller number of entities, or what we call the containers into Cosmos, where we have grouped the data together. So we have the same data that we had initially in Postgres, but with a simpler schema into Cosmos DB. And just to give you an overview of what I was speaking about with Azure Data Factory, so you can see a sample of pipelines that we have used to migrate the data. And so you can see that you have the source of your data, which are some different tables into PostgreSQL. And we are using, in fact, the different steps into ADF to be able to group the data together. So you can see that at the bottom, for example, we are doing a join between PG classification and PG article classification, and then we are aggregating some data. And so we have an output data set here. With PG translation, we are just aggregating some information, and we have so another output data set. And then with the main source of data, which is PG article, we are doing a join with the first output and another join with the second output. And then we are exporting the data into Cosmos DB, which is in fact inserting into Cosmos, an array of JSON documents, which are the result of the different joins that we have done before. So it's something which is very, very, in terms of visualization, it's very easy to visualize, and it's a good tool, which is not too complex to use to implement this kind of ETL pipeline to move from one data set to another one. So I will let Rumen present you the different lessons that we have learned during this project.
Indeed, there were quite important lessons that we learned from this project together with the customer. Some of them were obvious because they were documented very well in the Microsoft documentations. Some of them we learned them by the hard way, but there are a few which are, I believe, very important to know, which are applicable not only for Postgre, but also for any kind of migration to Cosmos. One of them is the perception that we have an SQL API. It means that it supports all the SQL features. No, it doesn't. It's not SQL NC 99 compliant, and most probably never will be, because of the vast amount of features which doesn't make any sense for distributed databases, or because of some of the features requires too much compromise with the most important features of NoSQL databases, which are scalability and availability, low latency and performance. So one of the examples are the aggregations of dynamic values. Because of the distributed nature of the database, these kind of aggregations of calculated values are not supported to the full extent, because simply they are not easy to achieve with fully distributed system. And the second is that many of these queries are actually slowing down the whole performance of the engine, and as a best practice they should be avoided. One of them is one very common approach to have a big queries. Big means by lines, so hundreds of lines of one query with multiple subselects of multiple joins, and do many stuff together in one query. The thing is that the database has never been good in optimizing those kind of queries, because simply they cannot understand what are your intentions. So even doing a very smart kind of understanding of your query, it will never be performant if you do it yourself. So instead of putting 10 different queries in one big one and do 10 different joins and group by and order by, everything together, instead of that you can break it on several pieces. The perception that is from the past that queries are very slow and to do, like multiple queries, it's not very welcome, are coming from the old relational databases where even with connection pools, the I/O operations and the query themselves, they were not the most performant. But these kind of experiences with us the last 30-40 years, and the world has changed a lot. So now there is no problem with the current implementations, no problem to run several queries, and the penalty is not that big, and it's okay. Actually, it's lower cost from performance perspective and also from money perspective, because Cosmos is based on the resource usage, is to run several queries instead of one. Having said that, you still have to know the limitations of the SQL API that we have implemented. One of them is, for instance, the limit of the number of the joins in the same query. You can see that very typically not optimized query with 10 or 20 different joins, especially left and right joins, which takes an enormous amount of time for the database to bring all these cross sections between the different tables. Yeah, it's you don't see that, and it's very handy and useful. But actually, when we are talking about tens of users or hundreds of users, it doesn't really matter. When we are talking about millions of users, and when we're talking about multiple clients, not only one or two clients, that's a huge penalty for the parallelism of a database. And when the relational database scale only mostly vertically by adding more cores and more memory, in the NoSQL database, we are talking about scaling horizontally when we add more nodes, and those kind of nodes doesn't have a central component most of the time, which takes these dynamic values and aggregations to make calculations between the different nodes. So usually you have these kind of nodes and high performance compute, and it's not very welcome to join data from different, let's say, partitions, physical partitions, or even nodes. So that's why all these limitations, and you have to be aware that there is a good reason behind that. So the limit of the number of the joins, if you have more than, let's say, 7 or 10, it means that maybe your query is not correctly done. Maybe you design it in a way that there are too many relations between the different data, and you could limit it by put them together, so you can fetch all the data without making joins. And the second very important is that currently SQL API doesn't support left and right and joins. None of the outer joins, only the inner joins are supported within a document, not between the documents. So because we migrated from relational database where there are multiple joins left and right, as I said, to embedded documents. So those kind of tables are in one document. And then we do left and right joins, migrate them to inner joins. Then they increased a lot, more than 10, more than 15. And then from efficiency perspective, that makes no sense. It's also on the cost side. So please be aware of the number of the joins. That's making order by group by together. Maybe it's not the best practice. And also the aggregation of the dynamic values in general. So then we have to talk about the IDF pipeline that works most of the time with the data flow. It's visual and easier and simpler, but sometimes it have some limitations because it's a low-code, no-code solution, and it's better to use Databricks with the Spark connector and code-oriented approach for more complex ETL transformations. Then the last one that it's really important is to try to change your habits with the SQL databases and relational databases to not put everything in one query. As I mentioned, it's perfectly fine if you put some of this functionality in the code of your application. And that way you're going to relieve the database from some of these calculations like data transformations, some other calculations that are not related to the data itself. So you can prefetch and pre-calculate some of these values. And that's one of the ways to do that is to using a cache of already grouped values. That will first will be cheaper because you don't hit the database, and second it will be much faster because you're doing it in the memory. So this kind of optimized techniques are really important for NoSQL databases. I would like to point you to two resources which are very practical and very directly related to the migration. First is with the ADF and Databricks using a Python and Spark and code first approach, and the second one is more easier, quicker and simpler using ADF data flows, but eventually it might not fit to all your use cases. And of course, don't forget to check all the query limits because, as I said, it's not supporting fully SQL 99 and it is not intended to be. So be aware of all these things. Thank you.
Thank you.